Now I'd like to examine what happens to certain chosen points that will serve to illustrate what happens when we have a linear transformation. So remember that linear transformations take this form, where you have one vector and the transformation matrix acts on that vector and it spits out another vector. In other words, the transformation matrix takes one point in the plane or one vector in the plane and moves it to another position. Okay, that's the interpretation of this matrix equation here. Okay, but I want to ask, what happens to certain points around the axis here? Okay, it will, as I say, serve to highlight what's going on. Okay, forget this part of the diagram for the moment. Let's just choose these 4 points: the origin 0, 0, the point 1, 0 on the x-axis, the point 1, 1 in the xy plane, and the point 0, 1 on the y-axis. I want to know what happens to these points after we transform it under a generic transformation of the matrix A, B, C, D. Okay. Well, we can take each of our points as the xy vector and apply this transformation and see what we get. Okay, so I'm going to choose the point 1, 1 and do this one and find out what happens to it, and then the others I'll leave as an exercise. Okay, so remember that this is a 2 by 2 matrix and this is a 2 by 1 matrix. That's 2 rows, 1 column. So if you multiply a 2 by 2 by a 2 by 1, you should get a 2 by 1. Okay, so that's what we expect. We expect a 2 by 1. Now, to get the first element in this 2 by 1 matrix, we take the first row and multiply it by the only column. Okay, so that would be A times 1 plus B times 1. That's the first element. Okay, then the second element here is going to be the second row times the only column, which is C times 1 plus D times 1. Okay, so our 0.11 gets transformed under this matrix to this new vector A plus B, C plus D. And remember, you can always go back and forth between Cartesian coordinates like this ordered pair here, 1, comma 1 in brackets, to vector form. They're equivalent. So the vector A plus B, C plus D, that's the same thing as being at the point A plus B, comma C plus D. Okay, so you see that the point 1, 1 gets transformed to the point A plus B, C plus D. Or equivalently, the vector 1, 1 gets mapped to the vector A plus B, C plus D. Okay, and if you go down through all of these calculations, you'll find that the origin gets mapped to the origin. So the origin 0, 0, nothing happens to it under a linear transformation. It stays put. Okay, the point 0, 1 gets mapped to the point BD. The point 1, 0 gets mapped to AC, and this point 1, 1 gets mapped to A plus B, C plus D. Okay, the takeaway from all of this is that you'll notice that straight lines all get mapped to straight lines. Okay, there's no change in their form. They don't wiggle around the place or do anything strange or unusual. Okay, lines are preserved as lines under a linear transformation. That's where the word linear comes from, line. Okay, you'll notice that parallelograms get transformed to parallelograms. So parallel lines remain parallel. That's also a signature of linear transformations. Okay, we will explore what happens to the area of this parallelogram in the next video, but I want to point out just one more thing, and that's that you'll probably have noticed that the point 1, 0 gets mapped to AC. Well, that's just the first column of the transformation matrix. And the point 0, 1 gets mapped to the point BD. Well, that's the second column of the transformation matrix. So you can consider this transformation matrix A, B, C, D. You can consider this transformation matrix as telling you via the columns where the point 1, 0 gets transformed to, and the point 0, 1, where it gets transformed to. And we will see later on that if you know these two new positions, you can build all other points in the plane from these 2 points here. Okay, this will be explained later when we talk about basis vectors.